close you are from the sun, right? So the thermosphere is close to the sun. And it's also related to how the different gases in the atmosphere let radiation through or absorb it. So the composition of the atmosphere affects the temperature of it. And as we'll see. So let's try to explain this by each layer. I think I have there we go. Okay. So let's start with the very bottom. Okay. The troposphere is for our purposes, the most important one because that's where climate occurs. Okay. So maybe we don't have to worry about the other ones, but might as well, right? Because we're looking at the atmosphere. So the troposphere is the lower part of the atmosphere. That's where climate occurs because most of the gases are concentrated there. Right? That's why the pressure is the highest. Okay. So why do we see this interesting behavior that it gets colder as we go up? Well, the reason is that the solar radiation hits the Earth gets warm, and then as it re-radiates that heat out, it gets cooler. Right? So it's the warmest here in the bottom, and it's re-radiating and it gets cooler as we get to the tropopause. Okay. So now how the temperature increases in this next section? Well, the stratosphere is where most of the ozone is concentrated, and the ozone is an important natural compound that absorbs the ultraviolet radiation. Okay. And then you've heard that the chlorofluorocarbons are all compounds that humans made that destroys ozone. So there was a huge problem. That was actually a successful case study of humans actually getting together and regulating ozone, things that destroy ozone. Okay. So we know that ozone is important because it absorbs ultraviolet light. As it absorbs it, it turns that into heat, into temperature. Right? So that's why the temperature increases here, because this ultraviolet radiation is being absorbed primarily by ozone. So it's highest on the surface, and as this UV radiation is being absorbed by the ozone, then the temperature decreases. Right? So there we go. We explained this first two parts. How about the mesosphere? At the mesosphere, you get a big decrease in temperature. And that's mainly because there's very few gases in that layer. So there's still radiation coming from the Earth, but there's not that many particles to absorb. Right? So they decrease with the decreasing amount of gases. Then increases back again. Okay, and the reason it increases back up again is that in this area there's no more gas anymore, so the temperature is really related to the sheer solar wind, the solar radiation is coming in. So the solar radiation is coming in. Here it's really hot. And then the decrease again is due to, as you enter the atmosphere, is how the composition of the atmosphere either lets through energy or absorbs it, depending on what's in it. So we talked about ozone, and then here we'll talk about later on how carbon dioxide helps to retain some of this heat that normally would have been re-radiated back to space. Okay, good. So this reminds me of this stratification, right? We talked about stratification. We did our stratification lab, so this shows you the stratification in the atmosphere. Okay, so how about the dynamics? So we looked at the atmosphere, the composition. Dynamics is motions. So we'll summarize it with this four concepts here. One is the idea of convection. So the air masses are moved up and down based on their temperature. So as you know, a warm air rises, we have a hot air balloon, it rises, and colder air sinks. So it generates a circulation through the Earth. Okay. As this warm air horizon sinks, it affects its temperature. And then its temperature affects how much humidity it can hold, how much water it can hold. Okay. So adiabatic means that the air mass doesn't change the amount of energy it contains, but the temperature changes as it expands and contracts. Okay, that's what adiabatic means. And we see that the little picture here reflects adiabatic changes and that how that translates to change in climate. And it's something we experience here in the Pacific Northwest. So, in fact, it's not raining today, but the reason we have a lot of rain in the Pacific Northwest is partially explained by this image. here we have this mountain, so they'd be the Cascades, right? And the ocean brings all this air that has a lot of moisture, so it's been traveling over the oceans, absorbing water. And as it hits the mountains, it rises. Basically, it's flowing here, it's an obstacle, it rises. And as it rises, the air expands and it cools. As it cools, it can hold less water, and the water precipitates and rains. So here in Olympia, on this side is a lot of rain, right? And on the other side, once a lot of the moisture is removed, on the other side, as the air drops, it compresses, it gets warmer, and the moisture evaporates, right? So that's kind of a typical example of how rising air masses do this convection, and then this adiabatic changes that lead to the expansion and contraction of the air masses, explains local climate, or even global climate. In this case, local climate here, but we'll see later on when we look at the circulation of the masses throughout the globe, explains that. Okay? Oh, actually, I put it right here. Consequence of climate of this, right? Air masses are moving, they change temperature, they hold or release water, and then that determines climate, right? So movement of air masses throughout the world, condensation, precipitation, redistribute heat around the planet, and that drives climate. What more is about 62? I'll remember later. There was one more point, but we'll move on. All right. So right now we have this simple view, right? So air masses go up and down, but they also move horizontally. And as they move horizontally, they're affected also by the Coriolis effect. How many of you have heard of the Coriolis effect? So the Coriolis effect is simply is this deflection of the movement of particles. It could be water particles, big particles, due to the fact that they're moving over a rotating rotating mass, which is a planet. Right? So what we need to understand at this stage is just simply what is the consequence of the Coriolis effect. And the Coriolis effect is in the northern hemisphere, particles are moved to the right of their motion. So you can see here, if the intended motion is the hatched lines, the actual motion is to the right of that trajectory. And the southern hemisphere is to the left of the trajectory. Okay? I'll show you a quick YouTube video that sometimes it's easier to show it than to explain it. Actual physics are more complicated. When I took physical oceanography, it was like a whole week to derive the Coriolis effect and its consequences. So let's see, maybe I have it here. Coriolis effect. Okay. So why don't we do this?
Ball appears to follow a straight path from thrower to catcher. An object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by two people on a merry-go-round that spins like the Earth, but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher. Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve away. The direction of apparent motion is to the right when following the path of the ball. Now the ball is thrown the other way. Because the thrower is moving, the ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again. Let's look at a throw across the merry-go-round. Both people move with the merry-go-round. The ball is thrown. Although it flies straight, it appears to be deflected from its original path. Apparent deflection increases as the ball travels farther. In the southern hemisphere, rotation is clockwise when viewed from over the pole. Again, the ball follows a straight course, but its apparent flight path is diverted. This time, the effect is to divert the motion to the left. On Earth, all free-moving objects. This time, the effect is to divert the motion to the left. On Earth, all free-moving objects, including masses of air, are subject to the Coriolis effect. In the northern hemisphere, objects are diverted to the right, as viewed from the direction of original movement. In the southern hemisphere, the deflection is to the left.
So that's the Coriolis effect. And to put all this together, we see that this actual pattern of circulation cells of rising air and dropping air through the world's surface. So we have the convection, which makes the air masses rise and fall, and then we have movement away from the equator. And as as air masses move, they are deflected by the Coriolis effect. So there's a cross-section, and the cross-section shows, for example, here at the equator, rising air, moves away from the equator, then it drops. So there's this, the Cohadley cells, but essentially are these convection cells. And then this shows you kind of the top view, which shows that deflection due to the Coriolis effect. Right? So here, in the southern hemisphere, there you have the southwest trajectory, you see that deflection to the left, and the northern hemisphere, you see the deflection to the right. Okay. So that explains the kind of the rainfall throughout the planet, these cells. So you can see most of the rainfall occurs. I don't know how many red ones. Well, is this all color coded by temperature? So the warmer temperature colors indicate more rainfall. So a lot of the rainfall obviously occurs around the equator, indicating rising air, and then as that cools down, it releases moisture and falls. And then the arid zones are where there's mostly air that's dry, and so around the kind of subtropics, you can see the big deserts associated with this zones where the air is cool and is sinking and dry, and it's dry. And then we have, we see this pattern, but the patterns change seasonally, right? And why do they change seasonally? Well, first of all, we have different amount of solar radiation reaching different hemispheres. So hopefully you're familiar with this, right? So the Earth's kind of tilted towards, and the orientation is tilted towards the sun. And it's not necessarily the distance from the sun to the Earth that affects, that determines the seasons, but actually is a tilt, right? So in the winter, actually our winter, in the northern hemisphere, we're actually the closest to the sun in terms of the shape of the orbit of the Earth around the sun. But in the winter, in our winter, the northern hemisphere is kind of tilted away from the sun. So that's why we have the seasons. And this shows you the area where the equator is in terms of the amount of heat received. And it's not a geographical equator, but it changes, depends on the obviously the season and how much solar radiation reaches different latitudes, right? So this is where that intertropical convergence zone is located during the winter, our winter. Further south, and it kind of migrates up as the face that the northern hemisphere has towards the sun is tilted towards it as we get into the summer. So this various are pretty well understood. That explains climate. So let's move down now to the oceans. Okay, so the oceans are a little bit similar, but a little more complication. Okay, so here's a picture of the oceans. And the oceans, there's three ways in which the oceans affect climate. So it's a little more complicated than just the atmosphere. Okay. It's similar to the atmosphere in terms of the physical aspects. So just as the different gases in the atmosphere absorb and distribute heat, both in terms of carbon dioxide, other greenhouse gases, and also the water vapor, which is it helps store energy and distribute it. The oceans do a little bit more. Okay, so they absorb, store and distribute heat because they are all water, and then also because the albedo. Albedo is a term that it refers to the reflectivity of a surface. Okay? So the oceans and ice have a high reflectivity, so in that way they contribute to the distribution of heat. There's a chemical contribution which is due to the carbon cycle. And so the oceans are a big source and sink of carbon dioxide, but also methane, other compounds that are associated with the greenhouse gas. And biological, because there's an important biological contribution to their carbon cycle, the productivity of organisms and their decomposition. The productivity consumes carbon from the atmosphere to photosynthesis and chemosynthesis, and releases back to the atmosphere to decomposition and respiration. So all the things we're going to be considering as we study how the oceans affect climate. Okay, so let's talk about seawater. There's a lot of text in here. Don't worry too much about writing it verbatim. I just after class today, I'll post this online so you can read it in detail. So I'll just kind of give you the major ideas here, and maybe those are the ones you can focus on writing to know what the messages for this slide. The message is basically that salt water it's kind of complicated. It's a complicated compound. In fact, chemical oceanographers spend a lot of time just looking at the composition of salinity. So the definition is actually fairly simple. Is the total amount of ions, things that are dissolved in water, and the units are ppT, or also written as a percentage with an additional zero. In the lab, we showed you how to use a Y-size instruments, and they reported the salinity as ppT, parts per thousand. That's kind of the convention. But the new convention is actually a different unit. It's called, if you look at the recent literature, they'll call it PSUs, practical salinity units. Why? I'll give you the kind of quick answer to that. In the past, chemists would always complain that oceanographers use the term ppT for salinity, because parts per thousand means parts of one thing, a distinct thing, versus parts of another thing, like chloride in water. Right? But salinity is a mixture of a bunch of things. So chemists are like, that's not, the rigor is not correct. So Sherry gave up, and some years said, oh, okay, we'll give up. Well, we agree it's not a good practice to use ppT, so we'll come up with another term. And they came up with PSU. Whether people don't worry too much about it because the number doesn't change. 34 ppT is the same as 34 parts per thousand, the same as 34 PSU. So I just tell you that because when you look at the literature, you'll see all those different terms used interchangeably. All right. So an interesting thing with seawater is that even though the total amount of salts changes depending on where you are, so we're here close to the river, it could be 1 or 2, 10 parts per thousand. The ocean here off of the coast of Washington, maybe it's 34, 35. If you go to the Mediterranean, it's 37. You go to the Dead Sea, it's like 40. So the total amount of salts vary, but the recipe, the composition remains constant. So that all the different salts remain constant. Okay? And so we'll examine that in a little bit. So why do we care about salinity? Well, one is salinity is the major thing that changes the density of water in coastal systems. So when we did a certification lab, we added a lot of salt to the water to create those layers. In the open ocean, temperature is more important, but salinity definitely is important in coastal systems to affecting density, right? So it affects the mass per unit volume. And here's a little bit of discussion. We'll use this for the discussion when we talk about we debrief the certification lab. But this is called addresses the idea of certification. And what we'll talk about is the certification separates the identity of different water masses, also explains circulation. Right? I think you all saw that. And the last one is actually pretty important. Salinity contains compounds called, and what we'll talk about is the certification separates the identity of different water masses, also explains circulation. I think you all saw that. And the last one is actually pretty important. Salinity contains compounds called carbonates, which allow the water to maintain the same pH. So seawater, as opposed to fresh water, maintains a pH constant. It's about 8.2, a little alkaline. And is this carbonates in seawater that allow that. So if you had a seawater tank for your plant, for your fish, for your tropical fish, they won't really survive unless they have actual seawater. You can't just make seawater artificially. Most of seawater is sodium chloride. You just make sodium chloride, your fish will die. And the reason is because they need this carbonates to buffer the pH, having that changes. So this idea of constant proportion is really interesting. So you will examine it in more detail. So this is an example using a little pie of how much of water, marine water, is salt. So in this case, you have 1 kilogram of salt. So typically, full strength seawater is about 35 parts per thousand. In here, it's 34.8 grams per kilogram of water. Right? So you can see, so it's a little sliver of the pie. If you look at the pie and look at the composition of the salt, here are the major salts, and it's dominated by sodium chloride, basically table salt. Table salt accounts for the majority of it. And there's all these tiny compounds. And the carbonates don't even appear here. The carbonates are part of this tiny amount here, but they're again disproportionately important because they account for this buffering capacity. This is the same data here as this picture, but now as percentages. So here are the major components of salinity. These are the minor ones. The major ones account for 99.28%, and the orange is a tiny amount. And you can see the sodium chloride is 85%. So I always ask this to my students, if you had a saltwater tank, one of the most expensive things in maintaining these tanks is the water, right? You need to get this salt water. So if you looked at this, you can say, oh shoot, if I buy, salt is really cheap, so sodium chloride. And all this other stuff, sulfate, magnesium, calcium, potassium, they're not that, you can get it, you can buy them, And I can make a little recipe that's 99.28 close to seawater. But if you use it, the fish won't survive. And the reason is mainly because some of this, particularly the bicarbonate, are the ones that are responsible for maintaining the pH stable. And so it's really important. So one question, two questions I guess. One is, why do you think it's so constant? I mean, that was a big revelation when the story of modern oceanography was by this boat, the Challenger, I think it's called. They went all over the world. The Challenger. They went over the world and they sampled everything, water, the chemistry, the biology, and everything. And one of the things they found was this surprising thing that doesn't matter where you're in the world, the salinity is in constant proportions. It varies in total amount, but it varies in constant proportions. Is there any ideas why? What we have the hypothesis of why the salinity recipe is the same everywhere you go?
Maybe it allows for life, or something like that.
That's the one answer was allows life, but that's kind of a consequence, right? So you're right. I mean, a lot of organisms are used to this. That adjust to this.
Because the Earth's mantle and crust and the composition of the rocks and its exchange with the water.
That's a good hypothesis too. The one answer is given that salt comes from the rocks, right? It's the conversation. So as these rocks get eroded, they're releasing compounds, and your hypothesis that they're releasing in this kind of ratio.
Kind of like how the lakes in Croatia are blue because of the limestone content.
Okay.
But there must be like a similar rock structure in the ocean that maybe has because they're porous and the water moves through it and it has an ion exchange.
Okay. So it's an extension of that. So the hypothesis is correct in the sense that some specific lakes, some locations, you can deduce their composition based on the surrounding material, how that's being dissolved in it, right? The oceans are very complicated, and the complication is that things that bring all this stuff into the oceans bring them at different rates. So different rivers bring them at different rates. Some of this stuff comes from hydrothermal vents. the most difficult thing in understanding the oceans as a chemical system is the biology, because some of these carbonates and stuff are a result of the decomposition of organisms, and the organisms take a huge amount of calcium carbonate because they form shells out of it. So the biology has been kind of difficult to model and come up with why exactly this residue exists. Okay? So I'll tell you kind of what the current hypothesis is. Well, it's a combination of things. Is that there's different sources. The sources bring in compounds at different concentrations, and then organisms take them up and release them. But over millions of years, the oceans have reached what we call a steady state. That state of balance, right? So there's things that come in, but they're also removed. So the rate of input of all these compounds matches the rate at which they're removed. So that leads to this constancy of composition, even though there's constant change. Does that make sense? That's the term steady state means there's constant change, but the end result is constancy. Constant composition, because of long-term mixing in the bowl of the oceans, have reached this steady state. Okay, so the other one's a little bit of math. And some people I think said they were concerned about math. But math is important in science, right? So we'll start really simple here. So knowing that there's constant composition, so here's a little math question, right? So we know, for example, here, regardless of the total amount of salt, sodium is always 30%, right? I just rounded out, 30%. Thus, if we just measure one constituent, we can determine, the total salinity of it. And in the past, chloride is the one that's highest concentration. People used to just measure chloride. It's easy to measure is the one that's in large concentration. And they had a fudge factor because they know it's almost 55%, so they multiply by the conversion factor. So we're kind of doing that here. So why don't you guys give this a try? If there are 3 grams of sodium in 1 kilogram of seawater. Oh, here's an example, sorry. And then the next one's a question. Here's an example. Okay. There are 3 grams of 3 grams of sodium in 1 kilogram of seawater. So what is the salinity? So we know the salinity times 30% equals the amount of sodium, right? So if we simply substitute the numbers here, we know it's 30%, there's 3. So 3 divided by 0.3 is 10, right? So 10 parts per thousand salinity gives us 3 grams per kilogram of sodium. Okay, so why don't you guys try this one? What is salinity if chloride is always 50% and then chloride is 15 grams per kilogram? Raise your hand when you know the answer. What is it? So chloride is always half. Okay, so chloride is always half of total salt. So think about that. It's always half. So if the chloride amount is 15 grams in a kilogram of seawater, what's the total salinity?
7 grams.
You're going the other direction, right? Because salinity should be more than the chloride. 30, right? Okay, so that's how we did it. Salinity is always half, so salinity times 50% is 15. So we have those 2 numbers, so we're solving for salinity. So 15 grams divided by 0.5. Sometimes when people throw us off as the unit, so I think sometimes I tell people like, okay, you're buying the TVs. TVs are 50% off, and you paid $100 for the TV. What was your original price? What was it? $200. Right? So sometimes if you just change the units, you don't really need to do the calculation. Okay? I'll ask you something like this in the quiz, okay? So look at my slide, practice it, and you'll see it's practice your percentages. All right. So let's go a few things, and we'll take a short break. Okay, because we're moving into the ocean system. Right? Okay. So what we talked about the atmosphere. So let's talk about the ocean and how it affects climate change. The most important thing is this. We call it thermal properties. Okay, so water, compared to all commonly found liquids on the planet, has the highest what we call heat capacity. And heat capacity, I put the definition there, is the amount of calories needed to raise 1 ml of a liquid 1 degree Celsius. So that's kind of the convention on how to measure the calories needed to raise 1 ml of a liquid 1 degree Celsius. So that's kind of the convention on how to measure the heat capacity compared among different liquids. So water has one of the highest ones. So what does that mean? Well, it means that heat is stored in water. It's very effectively stored in water. It takes a lot of energy to warm or cool, change temperature of water. So a lot of it is stored in it. Lakes and oceans store heat. Because so much energy is required to change the temperature of water, aquatic habitats have less fluctuations than land. And in fact, most of the temperature readings that we take to determine the climate is changing is from the oceans. Because land changes temperature really quickly. Even in this room, people in and out of it during the course of the day, temperature in the air changes quite a bit. But in a water system, because it takes much more time to heat it and cool it, it's a better indicator of long-term changes. What else I put here? Okay, so large amounts of heat and increase of stored water changes phases. So when you go from liquid to solid or a gas, a huge amount of energy is put into it. And that goes back to what we learned about the atmosphere. When there's precipitation or evaporation, heat is converted to a different form, and as the water masses move, you can move that temperature elsewhere. This can help to redistribute the temperature. So the circulation of air mass, as we look in the atmosphere, but also water masses, the circulation of the oceans, help control climate, because it controls the temperature. And I put other things. Rainfall, for example, in the Pacific Northwest, it rains a lot, so it's actually much warmer than in a similar latitude. We go to the Midwest, it's super cold there, right? And the reason we're not so cold here is because all this rain, as it rains, heat is released, warming up the atmosphere. And the last one is relates because of the reflectivity albedo. When water gets really cold, the water structures from a crystal and lowers the density and floats. So an important part of climate regulation is this ice caps that we have that reflect the sunlight, and they're an important part of the climate regulation. Okay. Again, you'll see this, you write it verbatim, you'll see that in slides posted. I'll do this kind of quickly. Just trying to give you another explanation of why water has such a heat capacity. And I don't know how many of you have had a lot of chemistry, but this is just shows a picture of the water molecule in different formations, different models. And the main thing to show is that the molecule is asymmetrical and has asymmetry in terms of the charges. So there's a net positive side close where the hydrogens are located, and a net negative side here where the oxygen is located. So the oxygen, the opposite attract, and the water gets together. It forms really strong bonds, so the negative and the positives can orient themselves and forms a very strong bond. It's called the hydrogen bond. There's all types of hydrogen bonding, but the hydrogen bond associated with the water molecule is one of the strongest ones. And to change the temperature, temperature is a measure of the kinetic energy, how fast molecules are moving. So to break this bond takes a lot of energy. So that explains kind of high capacity of water. It takes a lot of energy to break these bonds and make the molecules move around, and that energy is associated with temperature. Here's an example, gives you guys the numbers associated with how much temperature is released or absorbed as the water changes phases. So in some chemistry classes, I think in high school, I don't remember doing it in my high school, but other people share that. You can heat up a water parcel and see how the temperature changes as you heat it. And as you change phases, for ice, liquid, to vapor, this is the amount of the amount of calories needed to change the phase, and the vertical lines indicate the increase in temperature once that phase change has occurred. But the plateau, this big plateaus, are the amount of energy that's needed to change the phase. So how much energy needs to put in the system to go from a liquid to a gas and from a solid to a gas. So this huge amount of temperature is what's released or absorbed as the phase changes. And so we put all this together, both the water and the air. So as water masses move through circulation, there's a water cycle, hydrologic cycle. It rains, it falls in the mountain, some of it freezes, some of it thaws. It moves out to the ocean, some of it gets evaporated. We saw the circulation in the atmosphere. Right now we look at the circulation in the oceans. So the movement of these water masses and as it exchanges their heat in different locations as it moves, it regulates climate. In addition to when it changes phases, when it rains, when it evaporates, and forms ice. Oh, okay. This is related to the. This is the stratification. So at some point I wanted to insert this first or stratification discussion. So this is a good time to do it. Yeah. Okay. So let's just introduce this. We'll take a short break, and then we'll reconvene and talk about the stratification lab. Okay. All right. So where are we now? So I talked about the oceans, and I talked about the reason they're important for climate is because they are all water, and the water has a high heat capacity. As it moves, it changes phases, energy is absorbed or released. Okay. The oceans are also layered, right? So there's also stratified. And this is an example of kind of what you did in the lab last week. So the deep ocean, we have the deep ocean, and then the surface of the ocean. So this two-layer system, and we have a thermocline. Thermal means temperature, and in the open ocean, the change in density are due to temperature, not salinity. So that's why it's different from what we did in the lab, which was salinity. But the stratification will be the same, right? So we have this two-layer system. And in a little bit, we'll explain the consequences of that and how that affects climate. But I'm going to introduce a few terms here. So if you look at the temperature, here's a temperature line. Usually temperature, the right one. The right. Temperature decreases with depth, right? This here, so because the solar radiation warms the surface. Salinity usually increases with depth. So sometimes it's a mirror image, but not necessarily. Temperature doesn't determine salinity, and salinity doesn't determine temperature. So we have to measure both. And that's what we're going to do when we're out in the field. Okay? Together, temperature and salinity determine the density. So here is, if you measure the density in terms of the grams per volume, this is how you see it, right? But they all indicate the same, that there's a barrier around 100, in this case around 100 meters, a barrier to exchanges of materials and also temperature. Okay? So think about these terms. In fact, why don't you write them down? Thermocline. Cline means gradient or boundary. So there's one that's determined by temperature, one's by salt, and together they determine one of density. And when we go to Bud Inlet this Thursday, we're going to determine this where they are or where are they? What the location? Okay. So let's take a short break. Let's take a 5-minute break. Take a stretch break, bathroom break. And when we come back, let's talk about your observations from the lab, and I'll be able to connect it now to the lecture, right? So you can take, and when you come back, look at your notes to refresh your memory what you did in the lab. Okay, I think we can get started. So I kind of abbreviated some of the questions in your handout for the lab. So basically they're here. So we'll look at a combination of audience participation and me lecturing. Right? So we'll start by maybe asking you, hopefully you have your notes with you. So the very first question was how does stratification affect the distribution of dissolved materials? To see it? Or even if you didn't, how do you think it does? So I'll draw a picture of what you created. I had this tank, and we had 2 layers, a little ping pong ball, and this was blue food coloring. So picture of what you created. I had this tank, and we had 2 layers, a little ping pong ball, and this was blue blue food coloring. So what do you learn about stratification in terms of how it affects the distribution of the zone materials and the particles? Okay, so the stratification itself is a barrier, right? So stratification itself is a barrier to dissolved materials. So the food coloring represents the dissolved material, right? So the dissolved material, so you have just a beaker with water, and then you added the food coloring. Even you add a little drop, just by diffusion, this whole thing would become right away would get blue. But it didn't here. I mean, we let it sit overnight. It probably will. You probably start getting. You can actually see a little mixing also occurring at the interface. But the sharp density discontinuity help maintain it. Right? So that's really important because as we talk about climate, you'll see there's a big important interaction between the deep sea and the surface of the sea. The surface ocean and deep ocean. The surface ocean is in exchange with the atmosphere. So let's imagine this is the ocean. So the top layer is in contact with the atmosphere, so it's exchange of gases. If you get stuff down here in the deep sea, it's separated from circulation from the atmosphere for the time it takes for this to be remixed. Okay? So that's an important part. In terms of particles, we put this ping pong ball here. The ping pong ball is set in an interface. So interfaces are really important because materials tend to sink. Even living phytoplankton, for example, tend to sink. So there tends to be an accumulation of material here, both living and non-living. So things that feed on it, like fish and zooplankton, can also aggregate here. And it's an important area of high biological activity and chemical activity. So if you're a scientist, an ecologist looking at the marine system, it's important to determine if the system is stratified and where the layers are, because it gives you information about where to sample and where important activities are. Okay, so that's number one. Okay, so how about number two? Number two was kind of interesting. You put it in motion. So we have the waves. I'll put surface waves, and then middle waves. And we compared the length, the height, and the speed. Right? So which ones were longer? The surface or the middle wave? So who says that the surface waves were longer? 1, 2 people? Okay, so just a drop. So we're looking at waves here, right? So once you start creating them, so how do the bottom ones compare to the surface ones? So you're saying that the bottom ones were longer? Okay, so like that? Something like that? Okay. Sometimes. Okay. Any other observations? I'll tell you kind of what I was hoping to see, and as a limitation of the experiment. Right? So when you first put it in motion, usually you get the surface waves tend to be taller, and they break. Sometimes they break out and spill over, right? And they seem to move faster, right? And have the shorter wavelength. Okay. But once you let it settle, maybe by the next time I do this, I say, once you let it settle, once you move it, and wait maybe a couple seconds, and once the system kind of slows down, how does each layer moving separately? And this is kind of what I expected to see. So I'll kind of tell you. I'll put it. Whenever I do this, people see different things, but I think this explains why. Okay? So what I'm expecting to see after it settles a little bit is that the surface wave should be longer wavelength, and the ones in the bottom should be kind of like this. Anybody saw this? Some people saw this. Okay, some people didn't see that. But I think the reason is at the beginning. Yeah, the beginning what you see is this thing kind of spilling over, and you have this thing. And once it settles, it kind of does this, okay? All right, so why do we see this? The reason is that the surface, the definition of a wave is energy propagating over two So this is moving between air and water. So when you create this big wave, it's because it's pushing towards air, which is very light, and then gravity is starting to restore the wave. So the top wave gets restored really quickly because it's, you get this wave shape, but the gravity is pushing on it, and there's nothing really to hold it. Whereas the bottom is moving between fresh water and salt water. And this is a little bit denser. So once you create a wave, there's more density to support the wave height. So you should see something like this. Okay. In terms of the speed, I think the people see which one was faster, the surface or the bottom? Was faster? Was moving faster?
Earlier, the top one was south of the bottom. So the top one would be east and the bottom is
Okay. Okay. Great. So similar to this, right? The surface got flattened really quickly, and then you still saw motions in the bottom, right? Okay. And that's analogous to, let's say you have two cards. One has weight, and the other one has very little weight. You push them with the same energy, right? So the one that doesn't have weight, it moves, and then the energy gets dissipated quicker, right? So it's a little bit of part of how the momentum is preserved, because they have different densities. Let's see what else we put there. Okay, so the mixing, I kind of maybe combine a little lecturing here. So I show you this because it's important to recognize that there's two layers. There's a freshwater and a lighter layer and a bottom layer. So it's the same as the deep sea and the surface of the ocean, right? Surface of the ocean and deep sea. Okay. So in terms of the composition, generally speaking, you expect the bottom waters to have more nutrients. Nutrients are things that feed phytoplankton. Sometimes can call fertilizers, but nutrients kind of more technical term. And there's usually more nutrients down here. Why? Well, as organisms fall, they decompose here, and there's no life for photosynthesis. So there's an accumulation of things that support photosynthesis below the pycnoplast. But phytoplankton need light, right? So light's on the surface, and they need nutrients that tend to be below. So there's generally little productivity unless you combine them. And the only way to combine them is somehow bring this deep water to the surface. And that's by mixing. Right? So we'll see anytime you get some mixing can be beneficial because it brings the nutrients to where there's light, and organisms have the best of both worlds. The downside, and you see things like in Antarctica where there's huge mixing, the mixing is so severe that actually can be detrimental. Why would it be detrimental? If you have phytoplankton here and there's a big storm that happened in the Southern Ocean, if you're pushed to depths that are really great and there's no light for photosynthesis, then you don't get enough light to be able to use those nutrients. Right? So too much mixing is not good. Mixing generally tends to be good. So anyways, the last one, I'll explain the formation of the Mediterranean. That's kind of interesting, and it leads you to understanding deep ocean circulation. So there was a stage in the experiment where you separated the tank, right, and you mixed this water, right, and you had the salt water, fresh water, and this, they call it intermediate water. And when you remove this, what you should have seen is this intermediate water move in like that, right? So all this water had intermediate salinity between the fresh and the salt. So it didn't sink to the bottom because it has some fresh water in it. It didn't go to the surface because it has salt water in it. So it reached its own level here in the middle. But what I wanted to illustrate is that it created motion, secondary circulation. The water moved in this direction to replace the outflow, and there's a quick movement outside of the when you remove the container, right? So as an example, we call thermohaline circulation. Thermohaline circulation is what drives the deep ocean currents. And it's because thermo means temperature. Thermohaline circulation is what drives the deep ocean currents. And it's because thermo means temperature, halo means salt. These two things affect the density. So when you get a water mass that sinks, it creates horizontal motion because it pushes the water as it sinks and creates movement. This is related to the Mediterranean. I kind of mentioned that because the Mediterranean, something really interesting occurs. You got the Mediterranean basin, and the Mediterranean is really tends to be warm. There's not much fresh water coming in, so it's almost like an inland sea, and it flows into the Atlantic. Flows into the Atlantic, and it's very interesting what happens because the Mediterranean, compared to the Atlantic, the temperature is higher than the Atlantic, which makes the density lower than the Atlantic, but the salinity is also higher than the Atlantic. So it's a little bit denser than the Atlantic. So putting it together, what happens when the Mediterranean water flows out of the Mediterranean to the Atlantic, it kind of does what you did in your experiment. So the Mediterranean water comes out, has this unique density, and it sinks, but it stays kind of in the middle. So the Mediterranean water retains its identity as it slowly mixes with the Atlantic. And you can be out here in a boat, sailboat, sampling that we're going to do next week. This Thursday. And as you go down with depth, you'll see the temperature decreasing as you expect. And then all of a sudden it will increase. I say, there's something weird there. It doesn't make sense. And then the temperature will decrease again. I said, how could you have temperature? How could you have warmer temperature below lower temperature? It doesn't make sense. And it'll make sense when you look at salinity, because salinity will go up as you expect, and then there'll be a peak of salinity, and it'll go down again. So this unique combination will tell you that it's the Mediterranean water. When I learned this when I was in graduate school, somebody told me that, during World War II, the German submarines would use this to get in and out of the Mediterranean, because the Strait of Gibraltar is really narrow, and Gibraltar is part of England, so they have a naval base there. So the submarines would basically go out, turn the engines off, and depending whether they're going to go in and out, they would position themselves at that particular depth. Right? So if they want to go out, they go close to the surface, so the net flow would be, they go deeper down, and net flow is out to the Atlantic, and the net flow into the Mediterranean would be at a lower depth. Great. Okay. So let's go back to our lecture here. So we're gonna discuss that. Let me show you a little bit of ocean circulation. I'll show the circulation on the surface and the bottom, then we'll talk about the field first. Okay. So the surface of the ocean, this surface part of the ocean, the circulation, is really wind driven. So next week we'll talk about the interactions of the ocean and the atmosphere, and you'll see how the surface currents are regulated by the wind currents. And then that also affects climate. Okay. So you can see here, the currents are in these big, thick lines. The red are the warm currents, and the blue are the colder currents. And the little arrows indicate the motion of the winds. So you can see some correspondence between the wind motion and the motion of the waters below it. Okay. So you get the circulation cells called gyres. So for a purpose to understand climate regulation, you can see that temperature is warms at the equator, so warms those water masses. As the water masses flow to higher latitudes, they release that heat, warming up those higher latitudes. A major example of climate regulation due to these currents is the Gulf Stream. So you can see here the water gets really warm in the Atlantic, and it goes up in the Gulf Stream, and that actually serves to keep the United Kingdom fairly warm relative to the land that's further to the east in Europe. So the Gulf Streams are major. I think you can see it here. It's color coded. Here's the Gulf Stream. All this red is the warm water that's being transported to higher latitudes. And for the sake of time, I won't show you the animations, but you can just, when you get to see my slides, you can just click on them. They're pretty cool. One shows you the ocean circulation, and the other one shows you how temperature varies at different latitudes. Okay, so that's the surface circulation. The ocean circulation is the thermohaline circulation, because it's not driven by the winds, separated from the atmosphere. So the circulation of it is driven by different factors. This top section shows a cross section around the Atlantic. So here's the Southern Ocean, Antarctica. Here's the Arctic Ocean here on the right. And what happens around Greenland and in the Southern Ocean, close to Antarctica, water gets really cold and also gets very dry. There's a lot of evaporation more than precipitation, so the water gets really salty, denser. It's very cold, denser, and it sinks. So you have sinking of water, both in the North Atlantic and the South Atlantic. Most in the North Atlantic. The major formation of deep sea water is in the North Atlantic. So as it sinks, it generates this circulation. Was there a question? And oftentimes this is referred to as the conveyor belt. It's not quite a conveyor belt, but as a simplification, it works to visualize it. So here's a top view. So the formation of that deep water mass is mostly here in the North Atlantic and also in parts of the South Atlantic, and that drives the circulation. So this deep ocean circulation takes on the order of about 1,000 years. That's kind of general residence time, how long it takes for the circulation to be completed. And I'm jumping a little bit ahead, but some of the ideas that the humans have thought of kind of geoengineering solutions to global climate change to save us some time is to find some ways by which carbon dioxide that's in excess in the atmosphere can be inserted into the deep sea circulation. So we can get it below the thermocline. It ends up in here, and then it's caught in here for about 1,000 years or more if some of the carbon becomes ocean sediments. Then it's sequestered for millions of years. How do we get water being connected? Right? So we have the surface of the ocean and the deep ocean. So how do we connect them? Well, there's some parts of the world that are called upwelling regions. And upwelling regions are places where water upwells. So the water comes from the deep sea and it goes into the surface. So why would that happen? Okay. You have the surface of the ocean, the deep sea, so this is rich in nutrients, and also carbon dioxide. There's a lot of CO2 down here. Okay. So how do we break the stratification? Right? So one way is to upwell. So when does upwelling occur? Well, upwelling occurs primarily when wind blows along a continent. So let's show upwelling here, and this would be the southern hemisphere. No, is it? No, right? No, sorry, this is the northern hemisphere, right? You should know because of the way the deflection of the water occurs. So in the northern hemisphere, if you have wind blowing from the north to the south, the deflection is to the west, to the right of the motion, right? So in this case, and that happens here in the Washington coast, Oregon coast, California coast, when you have a situation with wind blowing from the north to the south, the water gets pushed to the right of the motion because of the Coriolis effect. And then that forces water from the bottom to come to the surface to replace the one that's moved offshore. That's called upwelling. If the wind then shifts and blows to the north, the transfer then is towards the shore. And you get a pile of water on the shore, which leads to downwelling. Right? So a lot of the mixing occurs due to this process. There's only a few places in the world where there's this upwelling, and there happen to be some of the most productive parts in the world. So due to this process, there's only a few places in the world where there's this upwelling, and there happen to be some of the most productive parts in the world. So it's a color-coded map of where most of the productivity occurs in the oceans. And the highest productivity is purple. The next productivity is in green. So what is the pattern? The highest productivity is in 1, 2, 3, 4, 5 places of the ocean. And those are areas where there's upwelling. There's constant upwelling. There's deep water coming to the surface with nutrients. Nutrients and light leads to high productivity. And the areas that are the poorest are in the middle of the oceans, basins. The next productivity range is all the coastal systems. So if you put together coastal systems, they're where the most of biological productivity occurs. The upwelling zones and the coastal regions. Okay. So how does this connect to global climate change? On the one hand, is to recognize that the oceans is not uniformly productive. So for humans, they're interested in fishery, et cetera, et cetera. These coastal systems are really important as a resource. And they're particularly vulnerable to global climate change because of sea level rise. Shallow waters tend to warm up faster than deep waters, so that can affect their biota. But one of the important things I'm going to show you as part of this class is that the coastal system is a huge area where carbon cycling occurs. A lot of carbon is taken up through productivity because of this high productivity. A lot of it comes into the biota, and a lot of it is buried because the continents have sediment that are being constantly eroded, and some of that organic material is sequestered, is buried. The long-term geologic timescale carbon cycling depends on how much of that carbon is sequestered along the coastal region. And fast forward to the present, it's important to recognize the importance of the coastal zone in terms of carbon sequestration, how much carbon is removed naturally, and to not lose that process. Right? As we put more into the atmosphere, we also need to make sure the natural ways in which carbon is removed are still preserved. Right? So there are multiple reasons why we need to understand the coastal system. All right, great. And that leads to the estuary, and leads to, I have like 10 minutes to talk about the field trip, okay? So an estuary is a part of a coastal system, and is where fresh water meets salt water. So we have that here, right? This is where, hopefully all you're familiar with Olympia, looking north. Here's a capital lake, a capital, and the estuaries where salt and fresh water meet. Fresh water from the Deschutes River, ocean water comes in from Puget Sound. So this is the estuary, this mixing area. And we're gonna do our study just north of here's the 4th Avenue Bridge. And on the other side, you can see here's the Port of Olympia, here's downtown Olympia, and there's a farmer's market. We're gonna meet there and do a little oceanographic study there. All right, so okay, maybe the logistics first. Okay, so check for this, and then at the end of the day, you don't know still how to get there. Let me know, and tomorrow, or today, I can give you maps and stuff. Anyway. So this is a map of Olympia, farmers market, a three-way store. I guess this is a further view of it. So if you go here, the farmers market is up here. This is State and 4th, and State there's a bus depot. So if you take the bus, which is free in Olympia, it's just a few blocks away. Here is Anthony's restaurant. I can give you the address. People Google it. There's Anthony's restaurant there, and then the Port Plaza, observation tower, is a dock. So we're gonna meet at the dock at 9. So people ask about parking. You have to pay for parking downtown Olympia as you drive. The farmers market is not open, so spending parking, the parking lot there says 2 hours limit. So I guess at your risk if they check. I don't think they check in the winter, right? So that's where I'll park. And if it's busy in the winter, in the summer, that they put us, somebody walks around with a little chalk and make sure you're not there for longer than 2 hours. But anyway, so there's plenty of parking there. Okay, so we're gonna meet here at 9 on Thursday. And what are we gonna do? Oh, here's a even better picture. Okay, this is all are gonna be in the next slide, right? So I'll post this one. So here's the viewing tower, here's a dock, here's a farmer's market. Now we're looking north is to the left here. And what you're gonna do with the size of the class, there's gonna be 4 groups of 3. So once you form your group, each team is gonna do some measurements on the dock using the instruments that you saw in the lab. And the 4 docks that you're gonna be analyzing is one's at Port Plaza, then the group is just gonna walk to the Percival Landing here. And if people drove, hopefully at least a couple of you would drive and you don't mind taking other people with you. I'll send you to 2 locations here. There's a dock here by the Hearthfire Grill. There's another restaurant here with a dock. And then there's this East Bay, the Swantown Marina. There's another dock there. So we're gonna sample the water as it flows out, and that kind of flows out to the ocean by looking at this 4 locations. Okay. Once you complete your measurements on land, you're gonna go back to the dock here and wait your turn to get into the Evergreen has a boat, outboard boat. It's called the Mother Goose, and the Mother Goose is gonna sample 4 locations now with the axes of mixing from the river up to not very far. We'll maybe go to the tip of the peninsula. It's gonna be, it's never been rough. It's, if you just walk down Columbia, it's gonna be pretty calm. We'll be wearing vests, and we have a Jenna is gonna be the skipper. So it won't take much time. So once you do your land station, one group's gonna go here, do this one, go back. Second group will replace the first group. They'll do another station. So you get the idea. So each team, each person will do had a chance to be in the boat one time, get a chance to do a measurement on land. So you have two measurements, and then you give them to me, and then I'll post them, and I'll take you through the analysis. I already posted the handout for the future. Okay. So that's essentially what we'll do. Once you're done with the 2 locations, then you can leave. We did this with 2 groups last time. There was an AM and PM group. With the success of the class, we'll be able to complete everything in the morning, so 9 to noon. Then you'll be done for the day. Okay. Okay. So a little bit about estuaries and last minute, so to give you more idea, so why they're important. So I give a lot of lectures to the public about estuaries. And this is an estuarium here is a organization that does outreach. So I put a whole bunch of things here why we care about estuaries. So I highlight the ones that are relevant to class. But that's all relevant to class, right? So the first one is basically in terms of the natural services that estuaries provide are super important. They're super productive, so they can be very vulnerable to sea level rise and for humans to understand how they work and to protect them. And here's some hints of why. Habitat and nursery ground for many species. Most just come and live here, or they just use it and then leave. Also, as a buffer zone between the land and the sea, so things that happen in the estuary kind of protects the land from erosion from the sea, storms and stuff like that. Areas of high carbon sequestration. So when we talk about the carbon cycle, we'll examine that in a lot of detail. How living things are affected by global climate change, but in some sense, an important sense, is they also are part of how climate is regulated through the carbon cycle. The last ones are more about humans and the environment, right? So, and that maybe connects to because it's environmental studies. We're connecting to this human interaction. So we saw some of the implications of an understanding system in the Retreat or Relocate article. So humans love to live by the water. Right? So there's a disproportionate amount of concentration lives close to the water. There's resources, there's amenities, people like there. Seafood, recreation, and it leads to this tension, right? So people like to live there, but they create a lot of impact. So estuaries, coastal zones are very important for a bunch of different reasons, and they're heavily impacted by human activity. So it's interesting to study them, but for a bunch of purposes. Definition of what is an estuary? Pretty simple. This is a simple definition. Donald Pritchard gave this classic definition. Semi-enclosed body of water, so arm of the sea, embayment, semi-enclosed, protected, within which seawater is measurably diluted with fresh water. I underscore those 2 definitions, and I'll give you the quick rundown of why this definition explains why this area is so productive. To understand it, let's go to what makes an area productive, and by productive I mean explains why this area is so productive. To understand it, let's go to what makes an area productive, and by productive I mean the base of the food chain is productive. The phytoplankton, photosynthetic organisms are productive. So why are they productive? Well, for a photosynthetic organism to be productive, it needs light, water, fertilizer, right? You have a plant, right? How about in an estuary? Well, they don't need water because they're in water, right? But they need light, and then they need nutrients, right? Okay. So if it's semi-enclosed, what happens, the advantage of being semi-enclosed is that the river, because it erodes land, it brings a lot of nutrients with it. It also brings sediment, meaning things that are mineral that are not nutritious. So the phytoplankton will have a problem there because there's a lot of things they want to eat that come from the river, but they can't eat them because they don't have enough light. Right? So what happens when this water hits the estuary? Hits the estuary broadens, is protected, so there's very little mixing. And when there's little mixing, things are suspended, settle. So the particles that come from the river that are blocking the light settle, and the nutrients that are dissolved are available to be utilized. Right? So that's one reason. Okay. So, and diluted freshwater. So freshwater indicates that there's a source of nutrients. Source of nutrients and a way to get rid of the sediments. Right? So you keep that in mind. It'll get you a long ways. Okay. So we'll do a lot of phytoplankton. These are the things that are fueling the basically the food chain. Sometimes they're toxic, others reptiles. This is a mixing of fresh. This is it shows you the mixing of fresh and salt water. And in the experiment that you did in the lab, you added the potassium permanganate, and I was hoping you would see this two-layer flow. The water mass move in different directions. Well, that happens in an estuary. The fresh water has a net flow out to sea, and the seawater has a net flow upstream. And organisms take advantage of that. Some of the organisms that can't fight the currents, if they spend more time in the surface, they end up, going to sea. If they spend more of the time in deep water, they eventually get pushed up the estuary. So things like crabs take advantage of that. This is an image of what you would, I don't know, you'll see it. Sometimes you see this. This cloudy water is the river water coming in, and then sometimes a sharp interface as it hits the salt water, and things start to settle. It settles because of this issue of less energy, right? So you imagine a container full of sediment of different sizes. You add water to it, you shake it, and you let it sit. You can imagine things as the energy of mixing slows down, things start to settle, right? Slow down. So that kind of is happening there. And there's an additional thing that happens that allows the sediment to settle. Okay, look, you're going to be doing this. You're going to either be here or here. Oh, no, you're going to do both. Sorry, you're going to do both. This is the boat. So instead of Alberto, it's going to be Jenna, and you can take up to 4 students. You're not going to go very far, so each person will be maybe 15 minutes or 20 at the most. And then you'll be in the dock. Hopefully, it won't be like pouring like it was this time, but be prepared for it. So dress like that, okay? And this is that mixing. Yeah, it's kind of cool mixing. Okay, so the flocculation, I'm going to tell you about this. Okay, so it's funny because there's 2 major processes that lead to the settling of sediments from the river. And it's very important, right? Because with the sediments in the water column, there's no life for organisms to use the nutrients. Okay. So one way the minerals are deposited is by the lowering of energy. The other one is called flocculation. Flocculation is more of a chemical, physical process, and that's when particles come into seawater. Seawater has different ions, which have different charges. So particles that come in from the river acquire charges as they enter seawater. And opposites attract. So essentially, all those little particles that are coming from the fresh water flocculate. They form flocks, which are aggregates. They form aggregates, and then these aggregates have the density to allow them to settle. So there's 2 things that happen, right? So it's lower energy and the presence of seawater that creates this flocculation. 2 things: remove sediments, and then the nutrients. And I want to have the nutrients are dissolved, so the nutrients are going to settle. The nutrients are dissolved by coming in, and then they can lead to high productivity. Okay. We'll learn later on that in addition to the phytoplankton, there's a bunch of other things that contribute to productivity, like seagrasses, marsh plants, and that's why we're going to go to this wildlife to look at this later on in the course. I'll show you that later. This is just an example. This is quantitative information showing you that estuaries are some of the most productive. This is a list of different habitats and their productivity, and estuaries kind of almost the top. The most productive is coral reefs and kelp beds, estuaries, and estuaries. Their range is almost as high as cropland, intensely managed cropland. Okay, I'll just finish this. This is what you're going to measure, read the handout, and then we're going to go over it. But part of the write out to the reports to explain why you're measuring all those things. So I'll kind of tell you right now. So we're going to measure temperature and salinity with a probe. We're going to go in depth. So why? Well, what kind of information does that give us? Stratification, right? So we want to map the stratification. So we measure temperature and salinity, and you're going to plot it and see if there's a gradient, right? We need to know the light penetration. Is it really getting more light as we move away from the river? Right? Is there a zone where the plant have the best of both worlds? You know, the sediments disappear, there's more light, there's nutrients, so that may be zones where there's more activity. We're going to measure oxygen, right? Because oxygen is an indicator of photosynthetic activity, so we can use it as an indicator. We'll take a plankton tow, we'll collect plankton. We probably won't have time to see it because we're going to do the beach field trip next week, and then we'll do a microscopy to look at the phlegm. And then the tide, actually we're pretty lucky, you know. You guys heard about the king tides? You know what a king tide is? What is it? What's a king tide?
Because of the orbit of the moon and like the timing, the tides come higher at the highest point of the season.
Great. Briefly, king tides imply that the tides with the highest amplitude of the year. So the king tides. Okay, so where they occur, I should give a lecture on tides, but you know, I'll mention a few things. But just very quickly, has to do with the alignment of the sun and the moon. But we do have an alignment of the sun and the moon every new moon and full moon. So that's when you have the highest tides of the lunar day, or the lunar month. But king tides is a combination of being the sun and the moon being in line, and other things that contribute to the tides, such as the distance of the Earth to the sun and the Earth to the moon, and the angle at which all those celestial bodies align. So the hugest tides that you can get is when the sun and the moon are aligned, like you have a new moon and full moon, when the sun and the moon are closest to the Earth, and the angles are such that they all line with each other. But I think that doesn't occur, like it occurs every like 10,000 years or so. But seasonally during the year, there are the highest tides, they're called the king tides, that usually occur in the fall, like now. And I don't know if anybody saw yesterday, we're like, whoa, they're really high. And then while we're out there during the day, they're all going to be really high. So maybe we'll be at their king tide. Okay, great. So that's it for today. I just went over a little bit. So have a good lunch. Come back here at 1, and we'll get started with another popular media presentation. And we'll go over the quiz. Okay, have a good lunch.